Okay, let's get through some of these real quick. So this is from the technical sample that I sent out to you guys. And I'm just going to run through these, hopefully, pretty quickly. So, convert 3 pi over 5 to degree measure. The 3 pi over 5, because it doesn't have a unit on it, it must be radians. So we're converting those radians into degrees. To convert radians into degrees, we want to introduce degrees and put in radians. So we need an equivalent amount, top and bottom, and we know 180 degrees is equivalent to 3.1415 or pi radians. So that's going to be our conversion. It is handy that the pi's cancel. And 5 goes into 180. How many times does 5 go into 180? I don't know. 5 into 180. 36 times. Okay, so 3 times 36 degrees. So that's 90 plus 18. So that's going to be 108 degrees. Nice. I guess I'll call it 1. Convert 120 degrees into radians. We're essentially going to do the same thing, but this time we're trying to get rid of degrees and put in radians, so the radians goes on the top. Sorry about the dog. And degrees go on the bottom, but it's the same equality, pi radians being the same as 180 degrees. So our units of degrees cancel. I'm going to divide those by 10, and heck, I'm going to divide them by 6 while we're at it. Divide it by 6. So we end up with 2 pi over 3 radians. Okay, so we should be able to convert back and forth. We want to know the length of the arc described by an angle of 60 degrees at a radius of 15 meters. So we've got a circle, so third one. We've got some circle, has a radius of 15 meters, and we're going through an arc of 60 degrees. And we know our relationship that this arc length should be equal to our radius times our angle. It's our nice little formula for arc length. But remember, it's important that that theta be in radians for this to work. You can, of course, use any formula in either degrees or radians, but you'll notice if you analyze a formula that has degrees as its input, the conversion between degrees and radians is usually lodged in that formula somewhere, because radians are just generally more useful. 60 degrees is one of our standard angles, so we are comfortable, hopefully, with the fact that that is pi over 3 radians, so our arc length will be 15 meters times pi over 3 radians. Don't have to put the units down there, it's just fun sometimes. And again, remember the nice thing about radians is it's not a contaminating unit. So meters times radians isn't radian meters or something like it would be if it was degrees. It's because it's a ratio, it doesn't contaminate, so we can just multiply these and get, 5 pi meters. And 5 pi is a perfectly reasonable answer. Don't feel like we have to approximate that or convert that. Okay, given that the tangent is 3/5, or tangent of theta is 3/5, and the sine is negative, so if the tangent is positive and the sine is negative, we better be down in quadrant 3. That's why we're told this. And we're told the tangent is 3/5, so that has to be a 3 and a 5, but because we're in quadrant 3, they better both be negative. And we want to find the other 5 trigonometric functions. So we want the sine of theta, the cosine of theta, tangent of theta we're given. That's why we only want the other 5 as equals. So we also want the cosecant, the secant, and the cotangent. The nice thing, to find all of these, all we need is to have this other length, that radial length, and we'll get that from the Pythagorean theorem, that c is equal to the -3 squared plus the -5 squared. Do be careful, this isn't a 3, 4, 5 right triangle. That 5 has to be the hypotenuse for it to be a 3, 4, 5 right triangle. But we can still find that length c with a little Pythagorean theorem. So that's going to be 9 plus 25. So c squared is going to be 34. So c is plus or minus the square root of 34. And regardless of what quadrant we're in, our radial length is always positive, so we use the positive version. Now we can set up any of our sine, cosine, cosecant, secant, or cotangent, depending on which ratio we want. So we know our sine is going to be -3 over the square root of 34, and we're of course going to rationalize that, so -3 square root of 34 over 34. Our cosine is going to be the -5 over the square root of 34, which again we'll rationalize into -5 square root of 34 over 34. And the reason we had to be careful about it being in quadrant 3 is because if not, we'd have lost those negatives. So do be careful about that. That does make our cosecant the reciprocal of our sine, so I'm going to use the non-rationalized form because it's easier. Square root of 34 over 3, the secant being the reciprocal of cosine. So again, negative square root of 34 over 5, and cotangent to the reciprocal of our tangent 5/3. So the big thing here is, one, just remembering our ratios. We've dealt with them long enough that they're hopefully becoming fairly automatic. Making sure we're careful about getting our hypotenuse computed correctly, and making sure we're in the right quadrant so we have the correct positives and negatives. So, find the exact values of our expressions. So, let's do it over here. So, we want the cosine of the sine inverse of 5/13. I know I'm talking very fast. Ideally, you guys can either slow the recording down if you want to on the playback, but you can back up or pause me or whatever. So I'm going to stick with my fast voice. So we got to be careful again what quadrant we're in. We know sine inverse is only defined in quadrant 1 and 4, specifically the negative version of quadrant 4 between -π/2 and π/2. But because our sine ratio is positive, we know we have to be in these upper quadrants. So we're going to have our triangle in quadrant 1 because that's where those overlap. We know the sine is the y value over the radial value, or the opposite over hypotenuse if you want. And a little Pythagorean theorem will give us that other side of 12. This is our nice 5, 12, 13 right triangle. So if we want the cosine for this angle, we could use sine inverse to actually compute, or approximate anyway, what this angle is, but we don't actually care. All we're asked is what's the cosine ratio for this angle, and we already have the cosine ratio. It's 12/13. So the answer is just 12/13. And that's that whole problem. The key is making sure we understand what the symbology is and what it's asking us, and making sure, again, that we're in the right quadrant. Part B here, tangent of the secant inverse. Nobody likes dealing with secant and cosecant, cotangent, especially cotangent. But the nice thing is we don't really have to. The tangent of the secant inverse of 5, and we could work with that. It's not that much of a big deal. But the big thing we know about secant is it's the reciprocal ratio for cosine. So we can change from secant inverse to cosine inverse just by taking the reciprocal of our ratio. Because remember, those inverse functions are taking in those ratios. So secant's argument, or secant inverse's argument, and cosine inverse's argument have to just be reciprocals of each other. So instead of working with secant, I'm going to work with cosine and just change it up. We know the cosine inverse is defined in quadrants 1 and 2. We know that cosine is positive in quadrants 1 and 4, so the only place that this could possibly exist is in quadrant 1 again. And our ratio is our x to r 1 to 5, so we need a little Pythagorean theorem to find that other side. So 25, that's all, we should write it out. 5 squared equals 1 squared plus b squared. So 25 equals 1 plus b squared. So 24 is b squared. So b is equals plus or minus the square root of 24, which we could simplify and should down into plus or minus 2 square root of 6. Now, what do we want the plus or minus? Well, we know we're in quadrant 1, and because we're in quadrant 1, we're specifically going to use the positive version, but we always want to be careful about that. These start throwing some negative sides around, and sometimes these can get a little messy if we're not careful. So we want the tangent value for this setup. So tangent we know is y over x, excuse me. So the 2 square root of 6 over 1, or just 2 square root of 6. All right. Give myself a little more space here. Where's my hand right there? Okay. Oh, actually, we're all the way down there. Nice. These are very common questions. You had 2 of them on your sample for the sample for the last exam. You had some of them on that exam, and they were a little bit hit and miss. So they take making sure we know what it's asking us about. So make sure you practice those, because I would expect to see them. But we're given information about 2 angles. We're given information about theta, and we're given information about phi. Phi, we're told our sine is equal to positive 2/5, and we're in quadrant 1. So we're in quadrant 1, and our sine ratio is 2/5. For phi, we're told that our tangent is negative 5/12, and we're in quadrant 4. So we got to be down here in quadrant 4, and our tangent is negative 5/12, so that's got to be 5, and that's got to be 12, and we know in this quadrant that 5 is going to be negative. If we were up in quadrant 2, the 12 would be negative, and the 5 would be positive. So again, that's why we have to be told what quadrant we're in. So again, normally a little Pythagorean theorem will give us our other sides. So that'll be a 13, because it's our 5, 12, 13 triangle. Here we need a little Pythagorean theorem, but it'll be 5 squared equals 2 squared plus b squared. So 25 equals 4 plus b squared. So b squared is equal to 21. So b is equal to plus or minus the square root of 21, and because we're again in quadrant 1, we are going to choose the positive version. If we were in quadrant 2, we'd have to choose the negative version, so make sure you're respecting that. So this information is what we are given, so we are told that that is the case, that this is the information we know about theta, and this is the information we know about phi. Given that, we want to find out what the sine of theta minus phi is. Now, theta isn't 2/5. The sine of theta is 2/5. Theta is some angle. We don't know what that angle is. We could compute it with sine inverse, but we don't have to, and frankly don't want to. But we do know that we can take the sine of a difference and break it up into the sine of theta times the cosine of phi minus the sine of phi times the cosine of theta with our sine angle difference formula. It's one of the formulas that'll be on your sheet, but we have to be comfortable with how we use them. And then we know these pieces. We know the sine of theta is 2/5 because we were given that. We know the cosine of phi. We weren't told what it was, but we know it's 12/13 because we analyzed our given information. So we know what that triangle looks like, so we know what, 13. So we know what the cosine of phi is. The sine of phi we also know because we analyzed this, so -5/13, so -5/13. And then the cosine of theta's got to be the square root of 21/5 or square root of 21/5. So we did need to do all this analysis first so we can answer any or put in any values that we end up needing. So 24/65 plus, when we get those two negatives, 5 square root of 21/65 is going to equal 24 plus 5 square root of 21/65, and there's no common factors in all of those, so that's our answer. Then our tangent of theta minus phi, we're going to do basically the same thing. We know we have an angle difference formula for tangent, so we look it up and we see that it's the tangent of theta minus the tangent of phi over 1 plus, those signs alternate, the tangent of theta times the tangent of phi. And given our two analyzed triangles, we can find all that information. The tangent of theta we know is 2 over the square root of 21, 2 over the square root of 21, which I'm not going to rationalize until later if we need to, minus the tangent of phi, which has to be the -5/12. We were technically given that information, but we also could figure it out from our triangle now that we have it. That is negative, so those will turn into a positive momentarily. And then on the denominator, 1 plus 2 square root of 21 times the -5/12. And then the key is cleaning this up. It can be a little bit ugly to clean up tangents formulas just because there's more going on in them. I am going to change that to a positive, and then 1 minus because of this negative here. I'm actually going to go ahead and turn that into 10 over 12 times the square root of 21. But I don't like having all these fractions in my fractions, so I'm going to multiply top and bottom here by those denominators, so 12 times the square root of 21 and 12 times the square root of 21. You can simplify these in any way that you like. Just kind of be careful with it. So when the 12 square root of 21 multiplies in this first term, the square root of 21's cancel, so the 2 times 12 is 24, plus when it multiplies into this second term, the 12's cancel, we're just left with 5 times the square root of 21, so no more denominators in the numerator, that's great. The 12 times the square root of 21 multiplies by that 1, we get 12 times the square root of 21, and then when this 12 times the square root of 21 multiplies by the second term, the entire denominator cancels, that's nice, minus 10. And see anything nice clean up out of this? There's a 2 in both of these terms, but there's not a 2 in both of those terms, so yeah, nothing's... And of course we can't cancel out the square root of 21's because they're not in every term. So unless we wanted to multiply by that denominator's conjugate to rationalize it, which we technically could, but if you've got a multiple term denominator, don't rationalize it, just leave it. So that's our tangent of theta minus phi. Find the exact value of the tangent of pi over 12. Again, I know I'm going super fast, but pause me, stop me, slow me down, whatever you need to do. Find the exact value of tangent pi over 12. So tangent pi over 12. Exact value, remember, means we're not going to be using any calculators. You won't have scientific calculators anyway. But we could do this in one of two ways. We could use a sum and difference formula like we did above, or we could use half-angle formula. Half-angle formula would work as we can turn this into the tangent of pi over 6 over 2. So pi over 12 is half of pi over 6. So we could put that into our half angle formula for tangent. But I'm not a big fan of the half angle formula for tangent. And we have the option here, if we can find two things that add together to make pi over 12, like 4 pi over 12 minus 3 pi over 12. If those reduce into some of our standard angles, we could use that instead, and then use our tangent difference formula, and I like that one better, but either one would have worked. It's not always true that we can use both of them, or use either one, but 12s are nice, because they're half of nice things, and they reduce a lot, so 12s always give us a lot of options. Fifths and eighths and stuff give us a lot less options, so it's nice to take advantage of them when we can. So, and again, there are lots of other combinations. The 4 and the 3 make a 1 pi, but you could use a lot of different combinations as long as it reduces. This is probably the nicest one. So that will reduce into the tangent of pi over 3 minus the pi over 4, and then we can use our difference formula for tangent. It happens to be the same one we used before, so that's nice. So we're going to get the tangent of pi over 3 minus the tangent of pi over 4. The numerator always uses the same operation. And then 1 plus, the operation always switches in the denominator, the tangent of pi over 3 times the tangent of pi over 4. So tangent of pi over 3, it might help to draw our diagram. Tangent of pi over 3, up here at pi over 3 we have an x value of 1/2 and a y value of the square root of 3 over 2. So the tangent is going to be the square root of 3 over 2. So the tangent of pi over 3 is going to be the square root of 3 over 2 over 1/2, which will simplify into simply the square root of 3, which is nice. We'll have less fractions than the problem above. So the tangent of pi over 3 is the square root of 3. The tangent of pi over 4 is 1, so that's especially nice. Over 1 plus tangent of pi over 3 is again the square root of 3, and the tangent of pi over 4 is still 1. So that gives us a nice square root of 3 minus 1 over 1 plus the square root of 3, which again, careful about over canceling. If we wanted to rationalize, we could multiply by 1 minus the square root of 3, multiplied by the conjugate to clean it up, if we wanted to. But again, if you've got multiple terms in your denominator, feel free not to rationalize. Okay, then some solving. Let me keep bringing this down. I think that makes more sense. So some solving here. So find solutions over the interval. Always do be careful to find your full exact solution and then restrict it to your intervals. So our cosine of phi equaling 3/7. Now this isn't one of our standard angles, so this is something we would need either a table or some bit of technology to tell us what that cosine inverse is. Your ones on your test will either include a table of values or will be one of your standard angles, so that'll be advantageous. Make sure I'm in, we can do this in either degrees or radians. Oh, no, our interval is specified in radians, so I better be in radian mode. So I'm going to switch my calculator over to radian mode. Good. And then we will use our inverse function to give us our principal inverse. So cosine inverse of 3/7, cosine inverse of 3/7. I get 1.12 1.128. Why not? 1.128. Of course, we get that in, that's a nice angle in quadrant 1. We know it's in quadrant 1 because quadrant 1 stops at 1.57, half of pi. So 1.128 is nicely in quadrant 1. The ratio was positive, and cosine's positive in that quadrant anyway. So we're going to get that answer plus anything coterminal to it, 2 pi plus 2 pi k. But we also know we're going to get another answer down here in quadrant 4. And that one, we can either use the negative 1.28 that's here, or people like to give the other answer, the positive first rotation answer, which is fine. But since we know a full rotation is 2 pi, we can subtract the reference angle, the 1.128, so subtract the 1.128 to get that secondary answer. So I'm just going to do that. 2 pi minus, I'm going to use the answer from last time to get a slightly more precise response. So 5.155. So 5.155. And that seems like a reasonable angle to be in quadrant 4. Remember, quadrant 4 ends at 6.28, ends at 2 pi. So 5.155 plus anything coterminal. So that's your general solution. We're asked for solutions only within the first interval, and without a compression factor on here, it's actually fairly nice. We really didn't necessarily have to go to that much trouble because we're only going to get our 2 primary answers, but if there was a compression factor in there, we'd have to do more work. So it's a good habit to find the full general solution first. So our 2 solutions for phi are going to be our 1.128. If we added any full rotations, we'd be out of our interval, so it's not going to produce any other answers. But we do have to make sure we remember the 5.155. Any positive or negative full rotations are going to take us out of this interval as well. So that's our full answer. Because of the phase shift in the second one, we're going to have to be a little bit more careful. 2 sine of phi minus pi equals 1. Now, we could use the difference formula to split this up, but then we'd have a sine of phi and a cosine of phi. We'd have a sine of pi and a cosine of pi, which we could simplify, and that would be nice, but we tend to like, it tends to be best to have the single trig function when we're solving, so we're going to stick with that. So tend not to try to use our identities to overcomplicate these problems. And then we can just use our nice sine inverse to get our principal solution, and then make sure we break out into our alternative solutions. So phi minus pi is equal to the sine inverse of 1/2. The principal solution is pi over 6, but of course also or anything coterminal to it. That pi over 6 is in quadrant 1. We know the other place that sine is equal to 1/2 has got to be up here in quadrant 2, because sine is positive in those 2 quadrants. And this reference angle of pi over 6 has to match this reference angle of pi over 6. So that's going to make this angle 5 pi over 6, because they're adding together to make pi. It is nice to notice, notice that you have to do it a little bit differently to figure out the second angle for cosine than you do the second angle for sine. It's one of the reasons I always recommend draw the diagram and be careful about, okay, where else are the functions positive and negative. It'll generally help. So our other answer set can be anchored around 5 pi over 6 plus anything coterminal to that. Now, we haven't finished solving because we haven't solved for phi yet, but that's our general solutions for the sine inverse. As soon as we take that sine inverse, we open up to these all possible answers. So, add pi to both sides, and that's going to give us phi equal to pi over 6 plus pi is going to be, sorry about that, Mark, is going to be 7 pi over 6 after you get common denominators. It's 6 pi over 6 plus 1 pi over 6, 7 pi over 6, plus all possible rotations. And down here, again, add pi, and we're going to get 11 pi over 6 plus any rotations. Now here we have to be a little more careful because we had that phase shift. It's possible that that phase shift pushed these answers outside of our interval, so it is important to check. But the 7 pi over 6 is certainly within that interval, so 7 pi over 6 is one of our answers. And if we added another 2 pi, we would get to 19 pi over 6, and that's too much. It's outside of our range. And if we subtracted pi over 2, we'd be negative, so that would be outside of our range. So, okay, that's our only solution there. And actually, the same thing down here. This is in our first rotation, and adding any other rotations is going to get us either too big or too small. So we still only get those two solutions. We won't start getting multiple solutions until, or more than two solutions, until we start getting compression factors or really big phase shifts. But we still do want to be careful and find that general solution each time. It's just the right habit to have. So tangent of 2 theta equals 1. Tangent of 2 phi equals 1. No simplifying involved here, or at least no solving before we get to our inverse function, but our inverse function is going to be tangent. So our 2 phi is going to equal the tan inverse of 1, which is pi over 4. And the nice thing is, for tangent, our other answer would be down here in quadrant 3, because that's the other quadrant that tangent is positive in. And these answers are in line with each other, so instead of having two sets of answers like we did in these other problems, we get the one anchor point and then a smaller period. It repeats itself every pi radians, or if we're in degrees, it'd be 180 degrees. And that just jumps back and forth between our two answer sets, which is nice. But we do have to still finish solving for phi, so we're going to divide everything by 2, and we get our general solution of pi over 8 plus pi over 2k. Now, we were asked for our solutions, within the first rotation between 0 to pi. Pi over 8 is certainly one of those, but here these extra rotations start to matter because our compression factor made those extra rotations small enough that they're going to fit within our 0 to 2 pi interval. So for k equals 0, we're certainly going to get pi over 8, but when k is equal to 1, we're going to get our pi over 8 plus pi over 2, and get some common denominators, multiply by 4, and we get 5 pi over 8, and 5 pi over 8 is certainly also within our interval, so 5 pi over 8. If k equaled 2, we'd be adding 2 of those, so we'd be adding another 4, so that would get us to 9 pi over 8, and 9 pi over 8 is within our interval, so that's a solution. If we let k equal 3, we're going to be adding another 4 pi over 8, or if you want to be formal about it, 3 times your pi over 2, and then get your common denominators, multiply by 4, pi over 8 plus 12 pi over 8 is 13 pi over 8. So that's another solution. Move that over. So 13 pi over 8. That's the same thing we'd get if we just kept adding 4 pi over 8. So that's a nice way to do it. But if you want to do it formally, there's nothing wrong with being formal. If we go to k equals 4, we'd be adding another 4 pi over 8. So that would get us to 17 pi over 8. And 17 pi over 8 is bigger than 2 pi, so it's outside of our interval, so that's not a solution. And it's always good to check what would happen if we were negative, but it should be clear that pi over 8 minus pi over 2 is going to be too small. It's going to be negative. So that generates all of our solution. There is a nice generality that you generally get 2 solutions multiplied by your compression factor. So all of these have a compression factor, that B that we use when graphing, of 1. So we expect 2 solutions from that. We expect 2 solutions from that within the one rotation from 0 to 2 pi. But because that has a compression factor of B of 2, I would expect twice that many, 4 solutions. If you had something that said, say, the sine of 3 phi plus pi over, I don't know, 6 equal something, 0.8, I don't know, whatever it equals, then I would expect 2 solutions in the first rotation, but multiplied by the compression factor, I would expect 6 solutions. Now, that's not always the case, particularly if you have answers that fall on the axes themselves. You can end up with less solutions than that, but it's a good generality to have. Okay, one more on this page, and then we have the back page. I'm trying to keep this under an hour, so again, I'm trying to go quick, and I'm overloading my RAM. Sorry. Am I overloading your RAM too, because I'm talking too fast? Okay, so this 2 sine squared theta, I'm going to add that over cosine theta and subtract that over minus 1 equals 0. This looks like it's trying to be of quadratic type. It has a squared trig function and a non-squared trig function. So it's trying to be of quadratic type, but they're not the same function. One of them is sine and the other is cosine. And gee, it would be nice if they were both cosine. And we can make them both cosine using our identities. Remember that the sine squared of theta is 1 minus the cosine squared of theta. And then the rest of our equation. And now we have everything in terms of cosine. We have a cosine and a cosine squared, so we're going to be of quadratic type. We just have to clean this up. So distribute that 2, so 2 minus 2 cosine squared theta plus cosine theta minus 1 equals 0. So negative 2 cosine squared theta plus cosine theta, plus 1 equals 0. Now, I don't like having this negative out in front. It irritates me, so I'm going to multiply both sides of this by negative 1 and get 2 cosine squared theta minus cosine theta minus 1 equals 0, just to get that negative out of my way. Now that we're in quadratic type, ideally we can factor this. If it helps, go off to the side and write it as 2u squared minus u minus 1 equals 0, because that might be, or you even use an x if you want, because that might make it easier visually to factor. That would have to be a 2u and a u, a 1 and a 1. We would need a negative 2u, so that's got to be negative, and a positive 1u, and then those would have to make a negative 1. So it does factor fairly nicely. That means that we could factor this into 2 cosine theta plus 1 times cosine theta minus 1. It just sometimes helps to see it in a slightly simplified form, if that helps. But as soon as we have them as a product equaling 0, our zero product principle says we can take 2 cosine theta plus 1, set that equal to 0 and solve, and then take the cosine of theta minus 1, set that equal to 0 and solve. Whatever makes the factors equal 0 will make the whole equation equal 0. So subtract the 1 and divide the 2, we get cosine theta equals negative 1/2. Here add the 1, cosine theta equals 1. We know cosine theta equals negative 1/2. If we take our cosine inverse, that negative 1/2 is over here in quadrant 2 at 2 pi over 3. So we're going to get 2 pi over 3 plus anything coterminal. And we're going to get that other answer in quadrant 3 at either negative 2 pi over 3 if you want, or since we're looking for answers in the first rotation, it might be better to look at this answer, which would be 4 pi over 3, whichever one you prefer. So that's our other set, 4 pi over 3 plus anything coterminal to it. Cosine, where's cosine equal to 1? Well, that's a nice one. Even if we take our cosine inverse, we're going to get theta equals cosine inverse of 1 is 0, technically 0 plus anything coterminal to 0. There is no secondary answer because it's essentially, the two answers are coming together at that 0, so we only get the one anchor point. We still have infinitely many answers because of all the coterminals. So our solutions to this that are in our range from 0 to 2 pi, notice again we found the general solutions first, but our solutions are going to be the 2 pi over 3. Any additional rotations are going to take us out of that. 4 pi over 3. Any, again, additional rotations are going to take us out of the interval we want. And 0. So the big thing is making sure we handle it like a quadratic. Noticing that we have a squared function and a non-squared function should make us think about quadratics. We do have to convert it into a single type of function, and then just be careful about your solving technique and your factoring. Okay, where's that other page? There we are. Ooh, lots of stuff on this other page. It's fun stuff though, but okay, so this is going to be at least an hour. That's okay. So, use the given values to determine the missing values for all possible triangles. As soon as you hear that all possible triangles, a little bell should go off that says, hey, be careful about your ambiguous case. So, do be careful in both of these when you're using your sine inverse to make sure you're respecting your sine inverse. So it doesn't matter how we label these. I'm going to call this the 55-degree angle. I'm going to call this angle B, this angle C. So if this is angle A, that means this is the side we don't know. This is the side length C, and that's the side length B. So that's what we're told. Because we don't have an opposite pair here, we don't have an angle and its side opposite, I'm not going to be starting with law of sines. We have essentially our law of cosines set up. Our law of cosines says, and again this will be on your formula sheet, that a squared equals b squared plus c squared minus 2bc times the cosine of the angle opposite the a squared. That's why this tool is nice for building opposite pairs. So a squared equals our b, so 13 squared plus 9 squared minus 2 times 13 times 9 times the cosine of 55 degrees. Yours will tend to have standard angles in them just to make these not require the calculators and so forth on your test, but we should know how to handle them in either case. So our a squared is going to be 169 plus 81 minus, what's 9 times 26? That's why I have a calculator, right? I do too much in my head. 9 times 26 is, times 9, 243. 243 times whatever the cosine of 55 degrees is. So a squared is equal to 200 and, what's it going to be, 250? Yeah. Minus 243 cosine 55 degrees. Do be careful of not subtracting those. I mentioned that before. It looks like it would be nice to subtract them, but that multiplying by cosine 55 has to happen first. So 250 minus 243 times the cosine of 55 degrees is 244.6. 244.6. Surprisingly small. Oh, that's because I'm in radian mode. Ha 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 ha. Do be careful. I knew that felt wrong. $110, that looks better. 110.6. So our a squared is the 110.6. So our a is equal to plus or minus the square root of 110.6. Since we're talking about an actual length, we'll certainly use the positive version, square root of 110.6. So the square root of 110.6. And since we're approximating anyway, we might as well get a nice little approximation of that, which is 10.5. So how about 10.5? Okay, so we have that other side at 10.5. Now we know we need then either angle B or angle C. This is where we have to be a little strategic. It doesn't look like it in my diagram, but notice that that 13 is the longest side length by far. This is length 9, this is length 10, well I guess not by far, but the 13 is certainly the largest side length. That means this B is the largest angle. So I don't know if this angle is acute or obtuse. It's possible it could be obtuse. And I don't want to have to figure out whether it's obtuse or acute using law of sines, because law of sines always gives me two answers, one acute, one obtuse, and I want to know which one to use. So don't use law of sines to find the largest possible, possibly acute angle in a triangle, or you have to deal with that ambiguity. We know this angle C must be acute. Even though it doesn't look like it in our diagram necessarily, it is opposite the smallest side, so it must be the smallest angle, so it must be acute. So I am much happier using law of sines to find angle C than I am using law of sines to find angle B. Oop, B, I don't like B. That's the whole point. So that little bit of strategy can really help avoid issues with ambiguity. So we know the sine of that angle C in ratio to the 9 has to be equal to the sine of our angle A, 55 degrees, over its 10.5 length. And then we'll just solve for C. So the sine of C is equal to 9 sine 55 degrees over 10.5. So C equals the sine inverse of this 9 sine 55 degrees over 10.5. So sine inverse of 9 times the sine of 55 degrees, I am still in degree mode, so that's nice, divided by 10.5 is going to give us a 44, I'm going to say 44.6 degree angle, so 44.6 degrees. Now it's also, of course, going to give us, or C equals 135.4 degrees, but because we know it has to be acute, we get to ignore that fact because we were looking for the acute one. If we were finding angle B, we wouldn't know which one to use, and that can be problematic. So we know this C is 44.6 degrees. And then when we compute B, we can find it using the fact that the sum of the angles has to be 180 degrees and not have to worry about whether it's obtuse or acute, because it'll come out the way it's supposed to be, whatever that is. So 44.6 degrees and the 55 degrees, take that away from the total of 180, and we'll get what we need to get. So what's that going to be? 99.6. So that's going to be 70.4 degrees. Okay. So 70.4 degrees. Now, law of sines would have told us 70.4 degrees for B, but it would have told us 70.4 or 109.6, and we wouldn't have known which one, because it wouldn't have been obvious that it has to be the acute angle. But because we found the 44 unambiguously, we can use the fact that they have to add up to 180 degrees to not have to worry about whether that 70 is acute or obtuse. It'll come out obtuse if it's supposed to be obtuse. It'll come out acute if it's supposed to be acute. So a little bit of strategy can help deal with that case. Okay. Now our other triangle here. If this starts to get too slow, I'll have to break this into 2 videos. I don't want to have to do that. You don't want me to have to do that, but let's see what happens. I'll get one more in. Well, I'm certainly not going to be able to do the vectors too. Okay, so I'm going to shut this video down. The application one might have to be 2 as well, because those take a while to go through. So we'll break this into a couple of different videos so I can take some time going through those. Okay, talk to you more in a bit.